direct measurement of the organic compounds. So it's like think about as a unit. Like yes, we're used to presenting some sort of chemicals. So by the way, can everybody hear me good? Yeah? Can you hear me good or okay, perfect. Okay. Yeah, so the idea of oxygen demand, right? It's another unit where it's another unit established by the environmental engineers, right? In the field, especially for those who's working in the field of maybe environmental analytics, sorry, analytical chemistry, for instance. But we're so used to representing units in something like mass per volume, right? If you're talking about maybe wastewater, right? It's straightforward that we're talking about some sort of mass like milligrams, right, per liter of whatever the matrix you're dealing with, right? So the idea of COD is pretty much the same. So what it does is we take the organic compound, we let it. This is like a theoretical approach mostly. So we let the organic oxidize in the presence of oxygen, and then which will be completely, oxidized to carbon dioxide, right? And oxygen reduction to water, obviously. So it's pretty much the same. It can be measured in two different ways. For example, we can do it theoretically, or we can do it analytically. Wastewater, right? It's hard to, no one's gonna see, like if you go to Gold Bar wastewater treatment plant, if you take some of the samples from there, they're not gonna give you the organic compound, right? They're not gonna give you organic compound like, C5H7 or something like this, right? You'll not be getting like the exact chemical formula of that organic compound. So that's why it's mainly done in analytically. So in order for you to measure oxygen demand, there are two different ways. Like one is COD, one is BOD. It stands for biochemical oxygen demand, and COD is chemical oxygen demand. So I'm not going to go through BOD today because I don't think in solid waste we're going to talk about BOD. But BOD is the same idea as a COD, just that we're using microbes. Just a little bit of explanation here. The reason why we go for COD, chemical oxygen demand, is a lot faster than BOD because BOD takes at least 5 days to get the result. But COD, for those who took 620 last term, you probably seen it in the lab, right? Or for those who's working with COD, if you use those kits, right, it takes like how long? About 2 hours, right? 2 to 3 hours. We can just measure the COD right away. Concentration of the organic compound in COD in like 2 to 3 hours, right? So when we talk about the theoretical COD equivalent, right? So there are 4 steps involved in it. So let the organic compound just oxidize, right, in the presence of oxygen. Just make a combustion reaction, set up the combustion reaction, and then you balance them, right? It's pretty much like high school chemistry that you do. Oh, I have a question here. Yeah, sorry, Osman. I won't be able to record the session because the course syllabus says I won't be doing recordings for the sake of, well, I'm okay with recording, but for the sake of the students, right? If I said something in the course syllabus, I have to follow unless I get 100% consensus on it. Sorry about that. You guys like losing signals or we good? Okay, perfect. So basically, you just simply balance. This is theoretically, first of all. And then, for example, let's say we're talking about acetic acid, right? And then let the acetic acid just set up a combustion reaction. Just simply balance it. I know I'm pretty sure you guys all know how to do this. And then convert the moles to the grams, right, of the oxygen that requires per mole or per gram of acetic acid, for instance, right? So if you just do the mass ratio between how much of, well, per gram, right? We're talking about per gram now. How much of oxygen you need to completely oxidize this acetic acid, for instance. So if you balance everything correctly, you should see 88. You need about 160 grams of oxygen required to actually completely oxidize 88 grams of acetic acid. So if you do the balance now, right, just the mass ratio, take 88 divided by 160 or 160 divided by 88. You can do it either way, doesn't really matter, but we can get the COD equivalent now. So we can now, if you do 160 divided by 88, then we get 1.8 grams of oxygen that you require to completely oxidize the 1 gram of acetic acid, for instance, right? So then if you're let's say if you're given mass concentration of your acetic acid, for instance, right? If you have 100 grams of acetic acid, you can simply use the COD equivalent to convert that acetic acid in the unit of COD. So if we have 100 grams of acetic acid, then we have 182 grams of COD per liter in the water, right? In the waste matrix. So just quick example. This was the acetic acid. I can't remember the other one. Sorry, what's C4H8 equal to? Oh, never mind. I forget. But anyhow, I think this is acetic acid. But you get the idea, right? So if this theoretical COD equivalent, once you know the chemical composition or chemical formula of that organic compound, then you'll be able to figure out what is the COD equivalent or the COD concentration that this organic compound exert on the environmental matrix. It can be wastewater, it can be waste, right? So this is just a simple example that you can go through your own, but the idea is pretty much the same. So basically, right? So
Kevin,
yeah.
are you switching slides? Because like we only see the first one here.
Oh shoot. Okay, I'm really sorry about that. You only see the first one?
Yeah.
Oh my. My bad, guys. My bad. Okay. So how about, whoops. Oh my goodness. Then I have to start from the scratch again. Okay, let me see if I can. Okay, how about this? You guys see it now?
Actually, no. We're still on the first one. Probably.
You guys
right
see it?
here. Yeah, we're good
Okay.
now.
Oh, god damn. Thanks a lot. Who is it? Alex? Or okay, I'm really sorry about that, guys. Okay. Okay. So basically it was one. Okay, so I'm just going through all the slide again. So but you guys got the idea by what I'm talking about though? So basically, again, right? It's impossible to track down all the organic compounds in environmental matrix. It can be water, soil, solids, anywhere, right? So that's why we introduce a term oxygen demand, right? So let the organic compound to go into combustion. Oh,
Next
I think
stop,
someone's mic is on.
Southgate Station.
Hanae, are you able to mute yourself? Okay, I'll just mute her. Okay, perfect. Okay, but you get the idea, right? What I'm talking about. So you just let the organic compound go into combustion reaction, and then you just set the combustion reaction, and then you can actually measure the oxygen demand, right? Can be theoretical, can be analytical, right? If you're trying to measure it theoretically, you're talking about balancing the reaction, like I probably have to go through again, but that's when you're trying to measure the COD of organic compound, theoretically, you will need to know the composition of organic compound, right? But in reality, right, you won't be able to know what is the exact chemical formula of all these composite organic compounds or mixture of organic compounds present in the let's say in this case wastewater matrix or environmental matrix, right? So BOD, I'm not going to go through it again. BOD takes longer time, a lot longer time than COD, right? BOD takes at least 5 days. COD takes about 2-3 hours for those who took 620 last term. So theoretically, assuming we know the organic compound, right? Assuming we know the chemical formula of the organic compound, right? You set the combustion reaction, simply balance it, right? So example, I don't know what the C4H2O2 is or H8O2 is. Can't remember on top of my head. It's definitely not glucose. I thought it was acetic acid, but but anyhow, this I'll just call it acetic acid for now, for the sake of the time, or simplicity. But anyhow, if you set the acetic acid under combustion reaction and then balance it, right? All what we're looking for, right? I'm pretty sure all of you can do this, right? This is based back in like high school chemistry. So you can actually find out how much of the oxygen that you need, let's say per gram of acetic acid, right? So if you do all the balancing, if you take the mass ratio of it, it turns out you need about 160 grams of oxygen per 88 grams of acetic acid for you to actually completely combust it, right? For the acetic acid to completely oxidize to CO2, right? And then once you get that mass ratio, right? Or we call it COD equivalent now, this mass ratio. Ethyl acetate. It's acetate, actually. Yeah, cool. Thank you. But anyhow, you can get the COD equivalent for acetate, right? So the COD equivalent will be 1.82 grams of O2 per gram of acetate. But you can actually, once you do that, you can actually convert this. You can write this as grams of COD per grams of acetic acid or acetate. So for instance, right, if you have 100 grams of acetate, that means your COD concentration of that acetate will be 182 grams of COD. So you could say, instead of saying 100 grams of acetate, right, or 100 grams per liter or milligrams per liter of acetate in the water, the 100 grams per liter might be a little too much, but you can say, instead, you can say, I have this wastewater or this waste stream has 182 milligrams per liter of COD or milligram COD per liter, right? So COD kind of cluster takes all these different concentration of chemicals or organic compounds present in the environmental matrix into just one single unit, right? Because depending on your chemical composition, right, your COD will be changing, right? But this is like the beauty of the COD, for instance. So these are the examples that you can probably go through. I think this is now methanol, if that was acetate, but I can't really tell. Again, right? So it's the same thing. You just do, you can just balance it and get your oxygen, right? How much oxygen did you need per gram of whatever organic compound you're interested in, right? And then it turns out to be 1.07 grams of COD per gram of, I'll just call it methanol. I think it's methanol. But anyhow, so instead of saying 100 milligrams per liter of methanol, you can say 107 milligrams COD per liter of COD that's present in the environmental matrix. Okay, so there are a little bit more example to it. So you can probably go through it. Oh, this is a kind of like a carry on. So once you have the COD equivalent, once you have the concentration in the mass unit, right, you can actually convert that to COD concentration. Okay, perfect. So nitrogen, I'm not going to go through it. Of course, if you have nitrogen, it will add on to your COD for sure. But I'm not going to go through it. This is the slide I want to go through. This is analytically done. For those who's in the wastewater lab, you've probably seen you probably know this, how to do this method, right? Analytically, right? So basically, if you want to measure the COD, so chemical oxygen demand, right? If you want to measure COD of this organic compounds or mixture of organic compounds, right? We really need the strong oxidizing agent, right? So if you look at theoretically, yes, oxygen is also strong oxidant or oxidizing agent, but maybe it might take very long time, right? If you're trying to combust it. But instead, we can use like dichromate or permanganate, which are like stronger oxidizing agents, right? To completely oxidize. So we have this little kit, right? I'm not sure if you guys seen it before. We in Canada, especially at U of A, I think across Canada, I think we use HAC or Chemetics. They actually provide like a kit for COD. Some in some lab they actually prepare like the oxidizing agent by themselves, like, right? You can actually simply use chromate or permanganate to actually completely oxidize those organics, but it takes about 2-3 hours, right? 2 hours of digestion time, and then you have to let it cool, and then you have to put in the spectrophotometers to actually get that COD readings of that organic compound. So analytically, assuming you don't know anything, right? Assuming you don't know anything about your whatever the waste sample, right? This is a really good tool to use. So talking a little bit of fractions of the COD, because the last example, yes, someone asked me about what's SCOD. It's actually soluble COD that I was talking about. We're not going to use that soluble COD because we're talking about solid waste, right? Solid waste doesn't really have soluble or particulate component to it. Yes, you could have it, but it's not really pretty distinct like wastewater. So the magic number that kind of divides between the soluble and particulate is that 0.45 micrometers. That's most people use that filter to filter out their sample to just measure the soluble COD. Obviously, you can measure the total COD, right, without filtering. And with filtering, you can measure the soluble COD. And then if you simply subtract it, you can get the concentration of particulate COD. So this is just the idea for that, right? Yes, obviously both fractions contain biodegradable and non-biodegradable component to it. So there's some little bit of fractionation. This is mainly for wastewater, so don't get tripped. All I want you to know is understand how the COD works. COD is actually the unit that we use, all the environment engineers use to actually describe the total organic compounds present in the environmental matrix. So this slide, I'll just probably let you go through your own. I don't have too much. I don't think you'll probably. It's this. I think the COD fractionation is not too relevant in solid waste. It's more for wastewater. So don't get tripped on it. Some solids. Again, I think most of you probably know about the solids, right? It's pretty straightforward, right? We talked about either in wastewater, we also talk about suspended solids and dissolved solids, but in the solid waste, we don't need to worry about it. It's gonna be either total solids or volatile solids. So it's a little bit more, it's less complex, but you can, for your information, you can just kind of go through the solid slides. But what I want you to know is, oops, keep going through. Oops, there we go. What I want you to know is the volatile solids, right? We talked about volatile solids versus the total solids, right? I don't know if you can see my cursor. So total solids includes volatile solids plus the fixed solids, right? So let's just don't worry about the suspended or dissolved. Just look at volatile solids or fixed solid, right? So total solids it means volatile solids, right? plus your fixed solids. Fixed solids are inorganic, volatile solids are organic, but we actually represent most of the time in the field of environmental engineering, we represent our microbes, sludge, as volatile, right? More exactly speaking, it's a volatile suspended solids, but we in solid waste we represent it as volatile solids because we don't really have dissolved solids, right? So this is kind of like just pretend you don't have suspended or dissolved solids in this PowerPoint slide. Here. Okay, so that's probably it. Let me see if I have more stuff. Yes, so this slide, I can kind of explain a little bit more. So filtering is fine because filtering has to do with either if you want to get suspended or dissolved. But when you actually ignite your sample, right, from your total solids, you can actually get the volatile solids, right? So because your volatile solids at maybe 500 or 550 degrees Celsius, volatile solids will be actually volatilized, right? Because they're volatile. So you're left with fixed solids. And then if you simply do TSS or TS minus your FS, your total solid minus fixed solid, then you can get your volatile solid. So just pretend you don't have the suspended part here. Just say VS is equal to TS minus FS. That's probably it. Yeah, that's probably that's all for the COD. So any questions about COD so far? Or volatile solids? I can see your chat, so if you put in the chat, that would be great. Does that make sense though? Like how great is in unit of COD, right? That we talked about because we're talking about the organic substrate. And the seed that we're talking about, so usually in environmental engineering, environmental engineering, or not usually, most of the time, almost all of the time, we represent substrate as in COD and seed, your microbes, and VS. Okay, so your microbes we actually presented as unit of VS, right? Grams of VS per liter or grams of VSS, like I talked about, suspended solids. Per liter of the environmental matrix, or per it's mainly water that we're talking about though. So it says conduct a COD balance if the final TCOD concentration is 15 grams per liter, and the experiment was conducted at 37 degrees Celsius, again mesophilic condition rate, and the total methane production was 1822 milliliter, and the total methane production from blank or the seed was 100 mil. Okay, so we are given this table, right? We're trying to design a BMP test now, right? So we're first of all, what we're interested is in how much of the substrate and microbes, right, the seed or the inoculum that we need to put in order for you to do the BMP test. So again, if you're given this table, right, don't get tripped on, right? Don't even look at the SCOD or total solid, right? These two columns, or sorry, the rows, right? You can just completely ignore it, right? Because your substrate you're dealing with is in COD, and your seed, yes, it has some COD concentration, but we're mainly worried about the VS content because your food to microorganism ratio must be in whatever grams of COD per grams of VS, right? So first of all, we have to find out how much of the feedstock and how much of the microbes we've put in our BMP reactor, right? Okay, so let's go there. Okay, so let me just get rid of that chat box. Oh, okay. No, I can't make it smaller, but anyhow. So we're given these two information, right? Again, your food to microorganism ratio in your assignment. Oh, by the way, your assignment is up. I already sent an email out last night. But regardless if it's assignment or midterm, I will specify your food to microorganism ratio for your question. But this this example, we're just assuming food to microorganism ratio is 2. And we picked, it's usually the bottle, right? The BMP bottle won't be that big. Like I talked about, it should be anywhere between 300 to 500 mil for your bottle volume or the working volume. So what you do is just simple, right? Just systems of equations, right? You just have two equations, two unknowns, right? Solve for V1 and V2, which will be your volume of substrate that you need for V1 is right representing how much of this substrate or the food that you have to put in the 500 ml bottle, and V2 represents how much of the volume of your inoculum or microbes that you have to put in your 500 ml bottle here. So it worked out. Please, if you go through this example and if you see typos, just let me know. But based on the solution, we get about 167 mil of substrate that we need per 500 ml bottle, and plus we also need about 333 milligram milliliter of inoculum per 500 ml bottle here. So once you figure out that part, now we have to kind of look at COD balance. The question asks you to design a BMP test, but also ask you to look at your COD balance, right? So COD balance, like I talked about, right? I kind of rushed through, but COD balance is really, really critical to actually see if your BMP test is is feasible or not, or reliable or not, right? So the actual methane production that we got from the question was 1,822 mil. But we also got 100 mil from just the inoculum, right? Remember, in BMP test, you must run control, right? Your microbes, right? It's coming from another digester, right? So they could actually contain any kind of residual COD concentration or any kind of residual organics that can be turned into methane, right, during the process. So we just have to offset it by 100. So our actual methane production just coming from your substrate is roughly just over 1,700 mil, right? And you calculate for your COD, initial COD, because what we want is how much of the COD has been converted to methane during this during this BMP test. But we're just this is a theoretical calculation now, right? This is the actual methane production, we got it. But now we're looking for the theoretical methane yield. So initially, right, this is a substrate, right? Substrate concentration, right, in COD. So by the way, these are all in COD concentration, right? Regardless if you're talking about substrate or your inoculum or your microbes, we're just talking about your COD concentration. So your total COD concentration, that what you start with, right? We have this much volume of that substrate, right? And we have this much volume for your microbes, right? So, or inoculum sludge, right? So we get about 12.34 grams of TCOD. That's what we started with, right? For your BMP test. Your final COD, right? In the question said 15 grams of COD per liter was left, right? After the BMP test, right? We observed there's a final COD concentration of 15 grams of COD per liter. So if you multiply by the working volume, or 500 ml, the bottle, right? That means our final COD in the bottle, right, was 7.5 COD, or total COD, right? And then if you take the difference between them, that's how much of the COD that has been converted to methane, for instance, right? So just approximately less than 5 grams of COD has been converted to methane now. So this is theoretical that we're talking about. So this much of COD has been converted to methane, but what we need is a methane yield, actually. So this methane yield, you probably all know, right? It's derived from the ideal gas law. It works for all the ideal gas, but your methane yield should be about 395 milliliter per grams of COD at 37 degrees Celsius. So I can maybe if you come to my office hour later on, I can show you how to drive this. But for your information, right, well, for your simplicity, you can actually use this methane yield. I'll probably provide you with the methane yield, the number during your exam, so you don't have to worry about it. But for your assignment, you should probably try to track it down, right, in your notes. But this is valid for 37 degrees Celsius. So once you have that, you can get your theoretical methane yield based on that just less than 5 grams of COD. Then you get about 1900, just a little bit over 1900 mil methane that's been produced from that COD here. So if you do the COD balance, for instance, right? So it's about 1700 mil divided by 1900 mil, and then times by 100, we get about 90% COD balance, right? So we talked about last time, this COD balance is totally valid because we are also talking about the microbial synthesis or biomass synthesis, right? So the microbes, just like human, right? We all can work, right? We all can work, but let's say if you have breakfast, lunch, or dinner, whatever, right? Yes, we consume it, and then we use that energy to do work, right? We go out and play outside, or we write thesis, right? We read books or whatever, right? But we also need some energy to maintain ourselves, right? We're not using 100% of the energy coming from our food, right? Just using it for our work, right? Because we also have to maintain ourselves as well. Same as the microbes, right? Whatever they eat, they're not gonna just 100% convert it to methane as their byproducts, but they're gonna use some portion of that methane as their cell synthesis. For instance, if they want to maintain their cell or they want to grow, right? These are all related to their biomass synthesis. So 5 to 10% consumption is totally valid for when we look at the COD balance or efficiency, right? So because this is just a chemical, right? This is just a chemical process, right? That we're looking at, but we also have to look at biologically, right? Because we're using microbes. So that's the last example that I want to go through. Any questions so far? Oops. So now we're just switching gears to collection system that I talked about. So this solid waste collection is a major component in the solid waste management or MSW management, because the waste collection actually, if you think about it, right, it's kind of weird, right? When I actually learned about solid waste, I thought about oh, maybe the processing cost, right? The solid waste processing would cost a lot more than just simply collection. But actually, waste collection, I knew at the end of the day, they can be a significant portion of the overall cost of solid waste management. So it actually contribute to 40 to 80% of your overall cost, right? Well, some of you probably had the same idea as me before I learned this stuff, but your processing cost doesn't cost you that much, but your collection cost really costs a lot of money. So that's why your solid waste collection become like a separate module in this course. So for instance, people in the developing countries, right, if they're using landfill for their waste processing as their waste processing facility, then we saw the cost like in module 1, right? The cost of landfill is so much cheaper. That's why most of the countries they're using landfill over other kind of technologies, right? So if that's the case, they might be just spending a lot less money, right? So they their collection cost, maybe it's closer to 80% of their overall solid waste management. But on the other hand, let's say maybe high income countries, right? In Edmonton, for instance, right? We're looking at various or different kinds of processing facility, right? So when we look at like anaerobic digestion, like composting, or it could be some thermochemical conversion, then we might be looking at about 40%. We might be looking at closer to 40%. 40% of our overall cost will be spent on your waste collection here. So, does anybody remember what is the cost? Like how much? I talked about it little bit more in detail. Does anybody remember what is the garbage cost for maybe? Let's start with the low-income countries. Do you guys remember that little table that we kind of went through in module 1? No, nobody. I know, chat. You guys are a little bit shy to put up in the chat, but in low-income countries, they're spending about 20 to 50 US dollar per ton of waste generated. On the other hand, in the high-income countries, right, they're spending about 85 to 250 US dollar per ton of waste generated, right? So for example, in Edmonton, right, I probably talked about this, but our garbage cost is about $50 a month, right? So if you look at yearly, right, we're spending about $600 per year for like a single family unit, right? So assuming you have like 3 people, average of 3 people, or it could be 4 people, right, per family, right? You're looking at about like 200. You're spending about $200 per ton of waste generated, which is quite a bit, right? So that is kind of directly related to your waste collection cost, right? So the city of Edmonton is spending about $200, right, for every ton of the waste they're collecting, right? Right, because we're paying that garbage fees in each household. But anyhow, that is like the cost side of the waste collection. But now, if you look at the environmental side or environmental problems of the waste collection, right? We're looking at the air emissions, right? We're looking at fossil fuel consumptions, right? So the reason why the waste collection has been really critical because it has to be really efficient. So you think picking up garbage is pretty easy. No, it's actually not, because there are a lot of engineering aspects to it. So, for example, like if the city were to collect waste in maybe downtown area, because I live in downtown, it's very, very crowded up here. But let's say if the city decides to collect the waste or solid waste in downtown, maybe during rush hours, right? Maybe 8 in the morning or maybe 4 or 5 p.m. in the afternoon. Would that be efficient to collect the waste at that time in the downtown area? Someone give me an answer. Thanks, Abel or Apple. Yeah, so no, right? So if the city decides to, collect the waste, right, during the rush hour in downtown areas, that's a really bad choice, right? Because first of all, your garbage truck will be stuck in the traffic, right? It will release a lot of air, right? And plus, it will consume a lot of fossil fuel, right? In Edmonton, it's impossible to, especially during winter, it's impossible to rely on like electric cars, right? Tesla, right? We mainly use, fossil fuel driven vehicles, right? So especially for the truck too. I don't think there's any electric truck made by Tesla. I don't recall on top of my head, but anyhow, right? You'll be wasting a lot of your energy. You'll be generating a lot of emissions to the air, so greenhouse gas emissions again. So engineering aspect has to come into play, right? So they could actually the city could decide, right? If you maybe down in far southwest, like maybe Rutherford. I don't know if you guys know a community called Rutherford down in southwest. Their area is pretty not crowded at all. So the city could spend their rush hour to picking up garbage from that area, right? While they can kind of come back or they can come back in the early in the morning or maybe towards like, just before noon or just in afternoon, they can pick up garbage in the downtown area so they can actually efficiently actually collect the solid waste, for instance. So that's why solid waste, you think there's not much of engineering comes to play, but yes, there are a lot of engineering aspects to the waste collections. So especially there has been some sort of research going on with it. So efficiently collecting waste, to efficiently collect the waste, people have been using like computer softwares like GIS. You guys heard about it before. Machine learning and artificial intelligence, AI, they have been playing a huge role in designing the routes or the routes of collection trucks. So these kind of aspects, right? It's all engineering aspects, right? They actually come into play, right? That's why we have like transportation engineers in our department who may be able to deal with these kind of the routing of the trucks, right? Or the dump trucks, right? So anyhow, these are kind of reason why this solid collection becomes really, really important. So that's why I said the understanding of process of waste collection it becomes important for minimizing cost, energy use, emission in the solid waste industry. So first important task is on-site handling and storage. So why is it important? Because city used to give us, right? I don't know how many of you live in, in a house, in a single house, right? But city actually provides, right, a bin, right? So back in the days, they weren't providing like the green bin, but now, starting from 2022 or 2021, they start providing the green bin, right? That's why they have the green bin program, so that we can actually separate. These are all part of the on-site handling and storage, right? So the city actually wants all the households to separate their non-recyclables, recyclables, and their compostable materials, right? Or a green bin, right? So we have three different, bins for if you're living in a single house, right? So you have a black bin, you have a blue bin, and you have a green bin, right? So it all depends, right, on what city kind of provides, city kind of decide to go with. But at this stage, we're talking about right. So if you're how much of compostable materials you're generating, how much of the recyclable materials you're generating, how much of the non-recyclable materials you're generating in each bin. So you guys all kind of, I think we talked about this in module 1, but you guys are all familiar with like the green bin, black bin, and blue bin, right? Or I think I talked about it in module 1. I just can't remember on top of my head. Yeah, anyhow, yes. So source separated organics will go to your green bin, right? All the other recyclables will go to your blue bin, and all the landfilling stuff will go to your black bin. So this is how you do on-site handling and storage, right? Whoops. So the first step, I know I talked a little bit too much about these, but the first step is, the first step in the solid waste collection, or before they collect, it's the on-site handling and storage, like we did. So it's an activity associated with the handling of solid waste until they're placed in the containers used for their storage before collection. So all the stuff, all the process just before the dump truck comes and collects your waste. So we'll look at a little bit of fun side here. I know if you go a little bit towards the back of this module, there are a lot of calculations to it, but right now we're just looking at some fun facts here. Well, some straightforward stuff, right? So residential buildings. So there are three main types, right? We have low rise, medium rise, and high rise. So anyone living in low rise, less than 4 story? It's Or you guys decide not to answer my question? Anyone in the medium rise? In a condo or no, nobody? You guys all live in high rise in an apartment? Oh, single house. Okay, perfect. Thanks, Cynthia. Okay. So I'll assume, oh, single house, single house. Perfect. Thanks a lot. Thanks a lot, guys. Um, so maybe is I'm assuming other people would be in mid-rise or high-rise. I'm in high-rise. I'm in an apartment. Yes, my whole family is in Calgary. We're in single house when I go back to Calgary, but I'm in a high-rise right now. But oh, apartment too. Thanks, Gilbert. Perfect. So let's start with low rise, like Hene is in whatever Tintia, right? Right. So it's a single or multi-family, family detached or attached, right? You were mainly talking about single house, right? The residents, right, are responsible for placing their waste into a storage containers, right? And then they have to take it out in the outside, right? And the homeowners or tenants, right, they're responsible for transporting the containers to out in the street by the curves so that the trucks and or the dump trucks can swing by and start picking up their the waste from people who are living in single house, right? This is more mainly for the residential stuff. But so the tenants and homeowners, they are responsible for just sorting the waste by recyclables, non-recyclables, and compostables. They're not required to separate the recyclables. All the recyclables of the separation of recyclable happens in MRF that we talked about, material recovery facility, but not at home. So for those who's in medium rise, they have large outdoor containers located in it usually because I've been to a couple of mid-rise before, but it's usually just hidden behind by the like the parkade or parking lot, right? So they have their own special areas, right? They have these big, you know, garbage bins, right? I don't know if it, no, I should say garbage containers, right? Sorry. So these big garbage containers, they're set outside in special areas. And then so you have to, all the tenants or the homeowners, they have to physically take your garbage and you have to dump it in this big areas. So you might see this more often in like a small like a mall. If you go I don't know if you've seen if you for those who lives in like White Ave, for instance, they have they have a lot of stores here and there, and then if you go to the back alley, you'll see a lot of these. You see a lot of these large outdoor containers. Um, so the thing is that I don't think they have a separate container for compostable, but what I know is they have a separate containers for all the recyclables. So high rise. So for those who's in apartment, you might see this, right? You might see the chutes on each floor, or you could also have a basement. If you go down to the basement of that high-rise buildings, you might see a big, large containers, garbage containers. But usually, yes, in old buildings, it's mainly the basement storage. But if you're in like a newer building, you'll see chutes on each floor. Unfortunately, I don't think they're in for the chutes. I don't think there's any kind of option to kind of separate your recyclables from your non-recyclables. But recyclables, I know in each building they have different kind of regulations and policies. My building has kind of regulations that you have to put your recyclables physically. You have to take it down to basement, and then you have to kind of throw in the blue bin instead. But most of the cases, just there's only chutes on each floor, right? You will not see any kind of options to, sort your recyclables from your non-recyclables. Even there's no option for composting as well. So you get the idea, right? High rise, low rise, medium rise, and high rise here. So, oh, Gilbert said something. Okay, we have different bins, but apparently nobody follows. Well, that's the thing, right? People don't really care too much about it, right? They just dump whatever they want. That's why a lot of, cities spends a lot of money, right? A lot of time to actually sort those recyclables from non-recyclables. Perfect. Thanks for your comment. So the reason why I talk about this, right, on-site handling and storage, because we have to actually find out what is the size of the containers or the garbage bin we require for maybe for low rise, medium rise, and high rise, right? Especially if you go to high rise buildings, right? There are a lot of people living there, right? So maybe if maybe solid generation rate maybe is 2,000 liter per day, for instance, right? But if the city gives maybe a container size, maybe 1,500 liters, right? It's not going to work, right? If your solid generation rate is really much higher. So if your solid generation rate is much higher than what the city kind of estimates, it's going to cause a big problem, right? Then your truck, they have to maybe send like a maybe bigger truck to take all the garbage, or your truck has to visit multiple times, right, to collect your garbage. So it kind of comes down to what is the container size that we need so that we can send out appropriate truck, the size of the truck, and we have to usually in residential areas once a week, right? Maybe in high-rise building twice a week for the garbage truck to pick up. But I've been seeing a lot of times, especially during the move-in, move-outs, I see our garbage can or outdoor or sorry, it's indoor for me, but our indoor large garbage cans are always full, and then people start putting the garbage on the ground too, right? There it's overflowing, right? Which is not desirable because your collection truck has a maximum capacity too, right? So it might in some of the days or some of the weeks they might have the visit more often than the other weeks, right? So that's why I kind of have this example here to kind of estimate the size and number of the containers that we need. Usually the collection happens, I'll be talking about this later on, but collection of the garbage happens once or twice a week. In the malls, maybe daily collection might be more appropriate, but in residential areas, once or twice a week, that's kind of like a usual case. So just let's look at the example. Again, the math is pretty simple, but it just gives you kind of the idea for it, right? So in a town, the average family size is 6. Calculate the size of the storage container for weekly collection of each family if the average waste generation rate is 1.5 kilo per person per day, and the waste density is 130 kilogram per cubic meter. So same thing, pretty straightforward, right? You can without even looking at the solution, you can probably calculate it, right? So total waste generation per week, right? 6 times by 1.5, that's your waste generation rate, times by 7 days a week, right? You get 63 kilo per week as your waste generation rate weekly basis, right? And then you can simply divide that by your density of the waste, and then you can get the volume of storage or the container that you need for that specific area that you're targeting. So again, another example, right? A community consists of 80 units with an average of 4 persons per, or not 4 persons, 4 people per unit. Sorry for the typo there. They are using one container for the waste, another container for recycled material. Calculate the size of each container for weekly pickup if the recycled material is 20% of the total solid waste generated, and the waste generation rate is 1.4 kilo per person per day, and assume the densities of the recycled materials and waste are 70 and 130 kilo per cubic meter, respectively. So you all got the idea again, right? So you just have to find out what is the total population, right? We're talking about now, right? 80 units. We have 80 units. Oops, I'm trying to get rid of the chat box there. But anyhow, 80 units, right? We have 4 people per unit, right? On average, We have 320 people. So total waste generation per week is 1.4. Again, the rate of solid waste generation times 320 times by 7 days a week. And we're looking at about 3,100 kilo per week as your solid generation rate weekly on a weekly basis. So 20% of that total waste is recyclable. So we gotta actually design these two bins separately, right? Now, just a little extra step here. So 20%, right, of that 3,100 comes down to about 630 kilo per week. And waste of this disposed waste, like non-recyclables, right? Or it could have some recyclables. So 0.8, right? 80% of that waste is disposed, going to landfill. So that turns out to be about 2,500 kilo per week. So volume of recycled materials, right? Simply divided by density, same as disposed waste, right? We're looking at about 9 cubic meter of the recyclable material. So we have to give something greater than 9 cubic meters for this community. Plus, and we have to give about 20 cubic meter of the volume volume container or container volume. Volume of container, not container volume, sorry. 20 cubic meter or something larger than 20 cubic meter, right? So these are the answers for your containers that we have to provide at least, right? This is something at least. I don't think there was any kind of safety factor because it's more you put it more. So for solid waste, I'll be talking about this later on, but for solid waste especially, we don't really need a safety factor, but it's more that you put in the volume, it's more efficient for the truck to pick up, right? Or the more efficient for the solid waste collection going to happen, right? Because you don't want the truck to leave, let's say if your garbage can is half full, you don't want the truck to just pick up the half of the garbage. That's a waste of time, waste of money again, right? So you actually want your garbage truck to pick up your garbage when your garbage containers are completely full. That's probably most efficient way of dealing with it. So if you keep building, let's say if we put safety factor, say I'm going to give maybe 15 cubic meters of recycled as a recycled container, then you might be just kind of wasting that 6 cubic meter, right? So you just want to be exactly at that capacity, so that or 100% capacity of that container, so that your collection, solid waste collection becomes more efficient. Again, so another example, community consists of 100 units with average of 3 people per unit. They're using one container for waste, another container for recycled materials. Calculate the size of each container for weekly pickup. If the recycled materials is 15 to 25% of the total solid waste, and the waste generation is 1.2 kilo per person per day, and assume these densities for recycled materials and waste disposal. So my question to you, so how can we design this? Now we're given a range of recycled materials.
I think we should go for 25 because it's better to calculate for the highest value. So that
Exactly. And how about your disposed waste?
that I don't know.
So we have a range, right? We're given range, right? The city is telling me that recycle for this community, recycle materials anywhere between 15 to 25%. So yes, sorry, I forget your name. I couldn't see your name, but one of your classmates said, yes, we have to design the recycled material for 25%, but how about your disposed waste? What do you think? Who votes for 75% for your disposed waste? Perfect. Tina, you got it. 85%, right? Because if we have to be conservative, right? So we don't know if this community will produce 15% of the recycled material all the time, or 25%, but we have to be conservative when we're designing, right? So we were being conservative with the recycled materials, right? 25%, but now we have to be conservative for your disposed waste, right? Assuming that your disposed waste in one of the weeks might be 85%, right? Perfect. Wasn't a trick question or anything like that, but it's kind of like, pretty intuitive, right? It's self-explanatory. So same thing, right? Calculate everything, right? Your total waste generation per week. And then you just have to find out what number you have to plug in to design your containers for your recyclable and disposed, right? So it turned out to be 9 meters cubic meter again for your recyclable, but your disposed waste has to be assuming 85% of your disposed waste you'll be producing out of that total generation of your solid waste, it becomes 16.5 meters cubed, which is a little bit different than the previous example that we did. Perfect. So any questions so far? Yeah, pretty simple. So I think one last example, yeah, I should probably go through this and then let you guys go. So the example reads total and separated, a little more complex or complicated, not complex. So total and separated waste produced from a household for each pickup are presented in the given table, and calculate the size of 3 containers, one for disposed waste, one for recycled paper, and one for other recycled materials, right? So this is like a typical example, maybe for the university, because at the U of A, we have a lot of different bins, right? For those who've been to campus, right? We have one for landfill, we have one for mixed papers, right? We have one for organic compostable organics, right? We have one for other recyclables, right? Like plastics, glass, and tin cans, right? You've probably seen at least 4 or 5 different bins at the U of A, right? So this might be a little bit more related to your reality if you're looking at just our university itself. But anyhow, we're given these, right? So we have total solid waste here. So not every component is 100% recyclable, right? So your food waste, they're not recycled, but your newspaper could be only 10% recycled, right? 10% of the newspaper might be recyclable, right? So we have to kind of design our containers for each different cases. So first, what you have to do is get the total solid waste generated, right? Total volume of solid waste generated for each component, and then calculate for another column. You have to calculate how much they can be recycled, right? And then if you take the difference between these two columns, right? You can get how much the